think we're good to go. So we're very happy to have Richard Eager. He's going to speak about maximally twisted 11-dimensional supergravity.
Thank you very much. So I will be talking about maximally twisted 11-dimensional supergravity. And this is based on joint work with Fabian Honner and work of other people as well for different sections. So the main motivation is to understand twisted supergravity, and a very inspirational quote by Kevin Costello and Natalie Piquet is that high energy theory and mathematics engage in a rich exchange of ideas from which the ADS-CFT correspondence has so far largely abstained. And part of the goal of this talk is to have this rich exchange of ideas between high energy theory and mathematics. And I think this conference is bringing people together from both math and physics, and I hope to kind of promote this exchange. So one of the key motivations for twisting, which is part of this conference, actually goes back to four-dimensional supersymmetric quantum field theory, and in particular, the relationship between the topological twist of 40n equals 2 super Yang-Mills, which is related to Donaldson theory. So Donaldson's study of the moduli space of instantons in Yang-Mills theory led to remarkable results in the study of differentiable four manifolds. And a careful analysis of the singularities in the moduli space of instantons actually led to the discovery of an exotic differentiable structure on R4. So prompted by Atiyah, Witten introduced topological twists and showed that Donaldson and Floer's theories could be described by a topological twist of 40n equals 2 supersymmetric Yang-Mills theory with gauge group SU2. And then, so that's kind of connection to mathematics. And then on the physics side, Seiberg and Witten described the low energy effective dynamics of 40n equals 2 supersymmetric Yang-Mills theory with gauge group SU2 in terms of an effective theory with gauge group U1 coupled to a magnetic monopole. So Seiberg-Witten invariants were easier to compute than Donaldson's invariants and led to further dramatic progress in the geometry of four manifolds. Similarly, twists of 60 supersymmetric Yang-Mills led to Donaldson theory and results for the enumerative geometry of Claviau manifolds. So a nice quote is that the physicists keep coming up with amazing equations for us to solve, us being mathematicians. Once we know the equations, we can get lots of mathematics out of them, but why can't we find the equations ourselves? So part of this talk might be considered a cookbook for mathematicians to come up with beautiful equations in mathematical physics coming from the pure spinor formalism. And while twisting had been very broadly successful for supersymmetric gauge theories, for twisted supergravity, a couple new innovations needed to be made. And the primary one I want to focus on is Costello and Lee's generalization of Witten's notion of a topological twist to holomorphic twists of supergravity and partial topological twists. And so their construction elegantly modifies the differential of the theory under consideration by taking their BV complex and adding a nilpotent supercharge, where BV is going to be the Bettelin-Vilkovisky complex. And to follow their recipe, we need to construct BV complexes for supergravity and choose a nilpotent supercharge. And rather surprisingly, both of these problems can be addressed using nilpotence varieties, which generalize the pure spinor superfield technique. So there's a very basic outline. We're going to define nilpotence varieties following work with Johannes Walscher and Ingmar Sabiri, and then kind of lightning review of supersymmetry in the BV formalism. And then we're going to generalize the pure spinor formalism to construct multiplets from equivariant modules over nilpotence varieties. And this is joint with Fabian Honner, Ingmar Sabiri, and Brian Williams. And this work is actually yet to appear. So it's going to be a little preview of that. And then we're going to follow Costello and Lee's procedure to twist 11-dimensional supergravity, which was joint with Fabian. Okay, so our first topic is going to be nilpotence varieties, and we can associate them to any supersymmetry algebra. And they have two primary uses that kind of combine both of the themes of this conference, which the nilpotence varieties parameterize all possible topological and partial topological twists of the supersymmetry algebra. And they can also be used to construct superfields and off-shell representations of the extended supersymmetry algebra. So maybe some familiar examples is the 10D n equals 1 supersymmetry algebra has a nilpotence variety, which is Berkowitz's space of pure spinors. And I'm always going to look at the projectivized nilpotence variety. And so this is actually equivalent to the orthogonal Grassmannian 510, which is a subset of the Grassmannian 510 of complex 5 planes in C10. And then there's going to be an additional restriction on which 5 planes are allowed, given by an orthogonality constraint. And a simpler example would be n equals 1 supersymmetry in 60, the nilpotence variety. So again, these are minimal supersymmetries, so they're just spaces of what we call Berkowitz pure spinors. So here the nilpotence variety would be P3 times P1. And in 40, the nilpotence variety is a disjoint union of two P1s. So a new example was actually defined in Martin's talk. So you can act, and it's a very nice toy example which illuminates many properties of nilpotence varieties and multiplets, is you take the supercharges Q to be 2 forms on C5, and kind of the generalized momentum to be 4 forms on C5. And the super bracket is just going to be the wedge product of the 2 forms, which will give you a 4 form. And then it's kind of a fun exercise to see that the nilpotence variety is the Grassmannian 2-5. And what I like about these nilpotence varieties is they show some very interesting connection to mathematics. And in particular, they are the only 2 Hartshorne varieties among rational homogeneous spaces. And it seems kind of like an odd coincidence that 2 of the most popular supersymmetry algebras have kind of a fundamental role in algebraic geometry. And the motivation for Hartshorne varieties is actually somewhat closely connected to the idea of twisting. So a Hartshorne variety is defined to be a smooth variety in Pn of dimension 2/3 n, which is not a complete intersection. And Hartshorne's conjecture predicts that this little n greater than 2/3 n is impossible. So it's about trying to be homogeneous spaces that are of large codimension and projective space. And it's actually quite difficult to do. And sort of the extremal examples of this are the space of 10-dimensional pure spinors in this Grassmannian 2-5. And a fun quote from Hartshorne is that while he's not convinced of the truth of the statement, he thinks it's kind of useful to have this particular problem in mind. So,
Richard, by impossible,
yeah.
By impossible, you mean larger dimension is a complete intersection? Is that what's impossible?
Well, so you can have complete intersections in any. Sorry, can you repeat the question?
What's Hartshorne's conjecture? It says that n is greater than 2/3, but
if that it's impossible to have a non-complete intersection.
Okay.
Of higher codimension.
Okay, thanks.
So kind of easy examples are like Grassmannians. So if you take larger Grassmannians, like Grassmannian, so let's see. So Grassmannian 2-5, is in P9 and it's dimension 4. So this is so it's dimension 4, which means it's codimension 6. So that's kind of a maximal codimension you can have. For example, you couldn't have anything of codimension 7. So I should say this little n is the related to codimension.
So the Grassmannian 2-5 is dimension 6, I think.
Sorry, yes, it's Grassmannian 2-5 is dimension 6.
2/3 of 9.
Which is 2/3 of 9. So this is the extremality.
OGR is more complicated because the dimension is
it's thin.
Yeah, so this is kind of an aside, but it's related to the fact that complete intersections actually have a natural multiplet, which is related to being a topological twist. And somehow these Hartshorne varieties are as far as possible from having topological twists. And kind of as you get further away from being a complete intersection, you have more interesting representation theory of supermultiplets. Okay, but yeah, so it's a really fun aside, and I liked putting this up because somehow these two natural examples that physicists sort of stumble upon are kind of related to somewhat deep conjecture in algebraic geometry. Okay, so I wanted to move on to the twist from nilpotence varieties. And so nilpotence varieties are actually stratified varieties, and the different strata correspond to different twists. And there's two main ways new strata can arise. One is from the fact that the nilpotence variety can be singular, and a singular locus is a interesting stratum. And then you can also have intersections of different components. And so I'll try to illustrate this with some examples. Kind of the most dramatic one, or one of the more dramatic ones, is the 5D n equals 2 nilpotence variety. And so it's actually a complete intersection of 5 quadrics in P15, and it's of degree 32, coming from the fact that there are 5 quadrics. So the degree is just kind of counting of intersection numbers. So each time you have a quadric, right, you take 2 to the 5th and get the 32 for the degree. If you kept on intersecting with hyperplanes, you would actually get 32 points if they're in generic position. And the interesting thing about this nilpotence variety is it's a disjoint union of 2 other nilpotence varieties, which from physics, maybe it's not too surprising. They're the 10D n equals 1 nilpotence variety and the 6D n equals 2 nilpotence variety. And so these also have a kind of interesting geometric interpretation of being linked in the sense of liaison theory. And a simple consequence is actually that the degrees of these algebraic varieties are additive. So this pure spinor variety is degree 12, and the 2D 6D n equals 2 variety is degree 20. And so they add up to 32. And you can actually translate representation theory of multiplets on any 2 varieties that are linked in terms of each other. So it's a little surprising that representation theory of the 10D n equals 1 algebra gives you certain results about the representation theory of the 6D n equals 2 supersymmetry algebra. And then there's a sketch of the stratification below. And so it's kind of, here are these 2 components, and they intersect over some kind of very complicated locus. And then this complicated locus is kind of some singular variety, and it has a singular locus, which is P3 times P3. So the singular locus corresponds to the holomorphic twist. And here, these 2 top strata are topological twists, correspond to distinct topological twists. And in between, you have a mixed, a partial topological twist. So some further examples that are going to be relevant for the later part of the talk is in 11 dimensions, the nilpotence variety is 22-dimensional, and its singular locus is the smooth variety, the orthogonal Grassmannian 511, which is the same as the orthogonal Grassmannian 612. And so on the singular locus, the unbroken symmetry algebra is U5, and it leads to the holomorphic, well, it's holomorphic in, say, 5 complex dimensions and topological in 1. So it's this holomorphic twist studied by Barry Williams, and I hope Brian will be talking about this in his talk later this week. And the stabilizer of a generic point, so this is kind of off the singular locus, is a parabolic subgroup with Levy factor G2 times GL2. And in physical language, so generic point is a spinor, and the spinor is going to correspond to a mixed twist that's holomorphic for the 40 n equals 1, and topological on G2. And so these have been studied in well, M-theory compactifications for a very long time. And the idea is to actually, in terms of computing things like corrections to F terms coming from G2 compactifications of M-theory, but we want to study them from the slightly different perspective of mixed topological twists. So kind of the motivation came from several conjectures of Costello, and we worked with Fabian, we derived parts of Costello's conjecture. Okay, so kind of going back to this recipe of Costello-Lee, first you need to pick a nilpotent supercharge. And so our nilpotent, so we discussed how we're going to use the nilpotence variety to pick a point that's on the generic locus, which defines the maximal topological twist. And then the second point of the nilpotence variety is to use it to construct multiplets. And so we want to construct a multiplet for 11-dimensional supergravity, and then follow the Costello-Lee procedure to twist. And the key ingredient is actually constructing what we call BV multiplets, because in extended supersymmetry algebras, you don't necessarily have complete off-shell representations unless you pass to the BV formalism. And just the general motivation for the BV formalism is that many important equations of mathematical physics arise from the critical locus of a degenerate action functional S on a space of fields equipped with some gauge symmetry G. And the BV formalism handles degeneracies by replacing the critical locus with the derived critical locus. And this is often handled in the physics literature by adding what are called the anti-fields, which is the key part of the BV formalism. And the derived critical locus comes equipped with an odd shifted symplectic structure, which is the anti-bracket. And gauge fixing in the BV formalism is achieved by choosing a Lagrangian submanifold in the space of BV fields. And the space of BV fields usually arises as sections of a graded vector bundle over the space-time, where the differential D is a differential operator. And so normally we call the Z grading the ghost number, and the Z mod 2Z grading the parity, which distinguishes bosons and fermions. Okay. So in this part, I want to explain how we use a generalization of the Berkovits and Sitterall pure spinor formalism to describe supersymmetry multiplets as modules over nilpotence varieties. And it is similar in spirit to the Borel-Veil-Bott construction of representations in terms of the cohomology of line bundles. And maybe in physics, the most familiar example of this Borel-Veil-Bott construction is that the spin J representations of SV2 can be realized as sections of line bundles over CP1. And the idea that we got from work of Martin Sederwall is that we just need to kind of a key input of describing multiplets is to give a free presentation of modules. And so this ring is always going to be correspond to a nilpotence variety, but I'm just going to set this up quite generally. So module M over any ring S can be described using a free presentation, which is just an exact sequence, where F0 and F1 are free modules, and the relations are encoded by the map phi, and a module M can then be described as the co-kernel of the map phi. And the kind of key input is going to be viewing phi as a matrix, which give relations to obtain M as a quotient from F0. And just taking this definition of the co-kernel, so we're always going to describe modules as co-kernels, but just writing out what it means to quotient, it just means that an element of F of M can be viewed as an element F naught, little f naught of this module, free module, up to a shift of anything that's in the image of phi. And so this is what Martin Sederwall calls shift symmetry, and it's very useful for constructing modules if you can find this type of presentation. And so for each equivariant module over a nilpotent variety, this work kind of constructs a general machine that will spit out representations of supersymmetry algebras. And I want to go through that in a simple example. And the first step of this procedure is you extend the free presentation of M to a free resolution by successively taking kernels. And it's kind of a classic theorem of Hilbert that these resolutions are actually finite. So before moving to 11-dimensional supergravity, I wanted to kind of illustrate this technique in 6D in a very clean example, which highlights the necessity of using the BV formalism and this kind of generalized pure spinor superfield technique. So in 6 dimensions, recall that the nilpotent variety, or the supersymmetry algebra, takes the following form, where you just have the anti-commutator. Also, the Q's are actually in the spinor representation, but they also have an R symmetry index I. And we have this super bracket. And this immediately leads to 6 quadratic equations, which describes the nilpotent variety as basically the vanishing locus of a 4x2 matrix, which is this matrix phi. And there's kind of a, right, so the minors, so these 6 equations you can actually view as the 2x2 minors of this matrix phi. And that's what's called a determinantal variety, and its projectivization is P3 times P1, which is the nilpotent variety. And this matrix phi actually can be used as the map for a free presentation of a module. And kind of naturally, just by looking at co-kernel phi, defines a module over the affine cone of P3 times P1. And if you push that down to the projectivization, this module, co-kernel phi, is the line bundle kind of O, 1 on P3 times P1. So it's just functions on P3 tensored with sections of the line bundle O1 over P1. And the component fields of the hypermultiplet are recovered by the minimal free resolution of the module gamma. So just to work through that, the minimal free resolution of gamma in R modules takes the following form, and it's a special case of the Buxbaum rim complex. And so here, this C2 is actually this R symmetry space. I decide not to give it a name. And then the S plus is the spinor representation. So we can read off. So this phi actually is going to be an R symmetry doublet. So it's a scalar. And then this S plus is going to be a fermion psi. And this, we can actually identify the wedge cube of S plus with the antifield of psi. And then finally, this last term is the wedge 4 is going to be a singlet. So it's going to be an R symmetry doublet and a scalar, which is the antifield of the first scalar. And so in particular, from the structure of the resolution, we see that it's necessary not only to have the scalar and the fermion, but we must necessarily include their antifields. And this is special to having extended supersymmetry. And we can go further. So I won't go through the procedure of basically breaking down so this is the pure spinor formalism, where we take the differential and separate it into two pieces. And the first piece governs the minimal free resolution. And then the second piece is kind of a correction. And anyway, this kind of work in progress with Ingmar, Fabian, and Brian. They'll go through this in detail, but it's very similar to kind of the work in Berkowitz's papers. And we can find representatives for what we call D-naught cohomology for all the fields, which is, and so they have a theta and lambda degree, maybe familiar from pure spinor formalism. And then from this, we can read off the non-derivative supersymmetry transformations. And kind of the key point for here is that there's a very interesting transformation that relates the supersymmetry variation of a fermion to that of its antifield. And this is related to the fact that the supersymmetry algebra only closes up to the equations of motion. And in particular, we recover the fact that this fermion satisfies the Dirac equation, the scalar satisfies the Klein-Gordon equation. Okay, so this is kind of a new example. I should say that the supersymmetry in the BV formalism in this particular example of the 6n=1 hypermultiplet was worked out in a very beautiful paper by Laurent Beaulieu and his collaborators back in the early 80s. And it was kind of nice to rederive their results using this generalization of the pure spinor formalism. Okay, so the idea is we want to take this machine and apply it now. So this is the machine that produces BV multiplets. And once we have the BV multiplet, we're going to twist it. And so the twisting of Castelli just works by taking invariants of a nilpotent fermionic symmetry Q, and the invariants are then the cohomology of that operator. So the relevant differential acting on operators of the gauge theory will be of the form S plus Q, where S is the original BV operator and Q is the nilpotent supercharge. And we just add them to get the new BV differential. So kind of the goal of the latter half of this talk is to derive Castelli's conjecture for the partial topological twist of 11-dimensional supergravity on manifolds M7 times M4 of G2 times SU2 holonomy. And so as a free BV theory, the twisted theory is described by a cochain complex, which is just the tensor product of de Rham differential forms on M7, tensored with the Dolbeau anti-holomorphic forms on M4, with a twisted differential, which is just the sum of the de Rham differential on M7 and the Delbar operator on M4. And kind of very importantly, there will be higher interaction terms. And one of the main ideas is to use Sederwall's description of 11-dimensional supergravity in the pure spinor formalism to try to drive Castelli's full conjecture. But for today, we're just going to look at deriving this field content for the free non-interacting theory. Or sorry, for where we disregard the higher interaction terms. Okay, so when we run kind of the pure spinor formalism, we get a very beautiful BV multiplet for 11-dimensional supergravity. And it contains the fields are in this theta degree. So the fields we have in lambda degree three, which are going to be a gauge 3 form, a graviton, and a Rita-Schwinger field. And the graviton has a vector ghost. The Rita-Schwinger field has a spinor ghost. And then the 3 form has a system of ghosts for ghosts, including a 2 form ghost, and then a 1 form ghost for ghost, and then a scalar, which is, I guess, ghost for ghost for ghost. And in particular, we also get all of the corresponding anti-fields for these fields just by resolving the structure sheaf of the 11-dimensional nilpotence variety. And the interesting thing is, just like in the hypermultiplet for 16 equals 1, there's going to be a nonlinear supersymmetry transformation connecting the Rita-Schwinger field and its anti-field, and it will necessarily be on shell and satisfy the Rita-Schwinger equation. So using the ideas of homotopy transfer that are in this work to appear, we can either derive or actually use this older work of Bergovitz to get the non-derivative supersymmetry transformations of all the operators in 11-dimensional supergravity. And kind of a very interesting thing is that many of the terms are nonlinear in the supersymmetry parameter epsilon. So for example, this variation is quadratic, and then these are all quadratic. And maybe the more familiar supersymmetry transformations, like for the physical fields, or for the bosonic physical fields of the 3 form and the graviton, are just linear in the supersymmetry parameter. But even for the Rita-Schwinger field, there's a nonlinear supersymmetry transformation connecting it to its anti-field. So the strategy is kind of quite straightforward. What we want to do is take the field content and the supersymmetry transformations and decompose them under the G2 times SU2 times U1 symmetry, and then modify the transformation rules by our nilpotent spinor. So the spinor representation in 11 dimensions decomposes as a tensor product of a 7-dimensional and 4-dimensional spinor representations. And we can further write them out in terms of a Lagrangian subspace in 4 dimensions. And so similarly, so that's the decomposition of the 4D spinor, but on a manifold M7 with G2 holonomy, the 7-dimensional spinor representation decomposes further as a singlet under G2 and a vector representation of G2. And so we can just describe or decompose the 11-dimensional spinor that we're going to twist by as, so this is going to be the entire 11-dimensional spinor as this contribution from 70 and this contribution from 40. Right, and then when we twist, we're going to just pick out a particular component, which is going to be a singlet of the G2 and also a singlet under the SU2. Right, so this is going to be the particular supercharge we twist by. And so we immediately see that this supercharge Q is invariant under the action of G2 times SU2 minus, and it has U1 L charge minus 1. And so kind of the first thing we'd want to do is write out the supersymmetry transformations in terms of this decomposition. And kind of beautifully, the normal space to the nilpotence variety is spanned by these supercharges. and they satisfy these anti-commutator relations. But the anti-commutator of Q with the Q alpha is 0, which is related to the fact that we have a holomorphic twist on the 4-dimensional manifold of holonomy SE2. Okay, so we have the decomposition of the supercharge, and so this is the charge we twist by. So we want to decompose all the fields, and we furthermore want to decompose all the gamma matrices because they appear in the supersymmetry transformations. And maybe just to remind you, the symmetric square of the 11-dimensional spinor representation decomposes as a direct sum of 3 irreducible representations. And we get projections onto all 3 factors, which are the gamma matrices. And essentially, so interesting thing, of course, is that we have wedge 2 and wedge 5, which correspond to the possible central extensions of the supersymmetry algebra, giving sources for M2 and M5 branes. And the important thing is we just decompose everything in sight. So we decompose the symmetric square and these vector and these wedge products of the 11-dimensional fundamental representation. And that essentially constrains all the gamma matrices up to scalars by Schur's theorem. And so that was kind of the level of detail which a lot of these computations go through. In principle, we could use computer algebra to nail down all the constants, but for the most part, we don't need the precise constants in the decomposition of the gamma matrices. So kind of an example of this, of how the computation goes, I'm not going to go into all the gory details, is we just take a simple field like the diffeomorphism ghost, and it's a vector, so it decomposes into a 7-dimensional vector on G2, and then it's a holomorphic, well, it's kind of related to holomorphic and anti-holomorphic components on R4. And we want to decompose the supersymmetry transformation that takes the vector ghost into the spinor ghost. And we see that 2 components of the spinor ghost are in the image, but 1 component is not. And so these two transformations are going to lead to cancellations in the twisted theory. And so these components will actually not survive, we say not survive the twist. This component's quite interesting. In a sense, it's not going to be in the twist of the BV multiple that I showed you, but it's actually going to be the leading component for a non-trivial module over the 11-dimensional nilpotent variety. Right, so this is just summarizing what I said. And then what we want to do is take all of the field contents and kind of in the paper, so this is coming from our paper, where each arrow shows a cancellation. So for example, this cancellation of the components of the vector ghost, so they're labeled by A, and so this component cancels with part of the ghost for ghost in C1. And so anytime there's a supersymmetry transformation leading to a cancellation, we just cross out those fields, and the remaining fields are all circled in blue. And of course, this is just half of the component fields, and they're going to be similarly the anti-fields as well. And essentially, this summarizes all the main computations of the paper. And the remarkable thing is, after you decompose all the supersymmetry transformations and take into account all the cancellations, the circle fields in blue precisely organize into this tensor product of de Rham forms on M7 and Bilbao forms on M4, or these anti-holomorphic forms on M4. And so you can kind of go back and see, in fact, that only parts of the three-form ghost system survived, and that parts of the Rarita-Schwinger field survived, and their anti-fields. So in particular, for this multiplet, the graviton did not survive, but as I mentioned, there's going to be one other multiplet that will play a role in when we turn back on higher order interactions. And the leading component in that multiplet should actually be this holomorphic piece of the graviton ghost. Okay, so then going back to the main motivation of the introduction, one of the main applications that we're looking forward to is applying this to twisted holography, which was the main motivation of Costello and Lee. And then there's already been several works that have just assumed this conjecture of Costello and Lee, or further conjectures by Costello, and kind of proceeded from there using lots of interesting homological algebra. But the idea is that once we get this bridge fully up and running, any result that's in this twisted holography program will be an actual derivation of a physical result. And one of my maybe personal motivations for why I was interested in twisted holography is that superconformal indices are kind of natural examples of invariance that you compute in holomorphically twisted theories. And so with Johannes Schmidt, we computed the superconformal index of ADS4 times a generic Sasaki-Einstein 7-manifold in terms of holomorphic data for the Calabi-Yau cone over the Sasaki-Einstein. And I've been informed that Costello and Raghav Andran are actually rederiving these results directly in twisted holography. And you can also consider superconformal index of ADS7 times S4. And another kind of beautiful application of the twisted M theory is you can couple it, especially the G2 factor, to a partial topological twist of 70 Yang-Mills and consider a G2 analog of Donaldson-Thomas theory and BCOV theory, which is already a published work of O, Del Zotto, and Zhao. And yeah, maybe before I finish, I should say there's also older work of myself, Johannes Schmidt, and Yuji Tachikawa, where we considered the superconformal index of ADS5 times Sasaki-Einstein 5-manifold and related the local operators to cyclic homology of that theory. And then very recently, there's work of Nikolai Babev and collaborators, Malik, Robinson, Sempleben, and Van Whedon, who derived the Klutzig-Klein spectroscopy for the Ley-Strassler superconformal field theory, and expressed that, and the results actually match computations of the cyclic homology of Michael Vandenberg. So these were field theory computations that with Johannes Schmidt and Yuji Tachikawa that derive cyclic homology. They gave local operators in terms of cyclic homology, and then they kind of maybe 8 years later, this gravity group could rederive them using EDS-CFT. But the hope is that actually using twisted holography, you can get a much cleaner derivation of all of these Klutzig-Klein spectra. and come close to giving a mathematical proof of ADS-CFT along a slightly different lines than Nathan Berkowitz's proposal. Okay, so thank you very much for listening. I know it's a little fast, but also sticking to the original.
Any question for the speaker? Please.
Could you say something, thank you for a nice talk. Could you say something about how you're planning to derive interactions?
Okay, right, so there is an older, so there's a very beautiful paper that maybe the main point of this talk should have been just to emphasize that there's a work by Martin Setterwall. It's something like manifestly supersymmetric 11-dimensional supergravity. And it gave an action for 11-dimensional supergravity in the pure spinor formalism. And a key part of that is he had constructed the action using certain differential operators. And so the idea is that these differential operators should be considered as some differential operators between various sheaves on the nilpotent variety. And the hope is actually that by studying these equivariant modules, we can not only, we can use the geometry to construct interactions. So one part I didn't say is that all these varieties have natural volume forms, and they have, if you have multiplets that pair, sometimes you can just directly pair to the volume form. That naturally gives you a way of producing interactions. And so part of it would just be trying to understand, first of all, the classification of multiplets. And for 11-dimensional supergravity, there's a very beautiful multiplet that comes from Chevalley-Eilenberg cohomology of super translations. And it seems like this multiplet starts with, it contains the holomorphic piece of the graviton ghost, and it also will contain a little piece of the graviton on R4, and that the Chevalley-Eilenberg cohomology gives you it's actually a rank 2 module over the nilpotent variety. And our hope is to kind of relate this module coming from Chevalley-Eilenberg cohomology to the differential operators in Martin Setterwall's work, and to use that to write down both the full BV action and then be able to twist the interactions. And as far as I can tell, maybe Martin can correct me, that the full expansion of the BV action for 11-dimensional supergravity has never fully been worked out. So it's kind of a beautiful open problem. And kind of, there's actually a reverse idea that I learned from Value Kano Singer is that sometimes there's a two-way street, and there's a procedure called untwisting where you do if you have a twisted theory and you do all the gauge fixing for it, all the terms you introduce by gauge fixing sometimes reproduces the untwisted theory. And so perhaps a different avenue is just by starting with this conjecture of Castello, and Castello, I should say, also conjectured the form of the twisted interactions, that you could try to untwist that theory and learn something about the full BV form of 11-dimensional supergravity.
Thank you.
Other question?
Can you say some more about the Chevalley-Eilenberg cohomology? Like what co-cycles are of interest?
Okay, so Chevalley-Eilenberg cohomology plays several interesting roles. So one, right, when they're singlet cocycles, there's some sort of Serre spectral sequence that lets you extend the algebra. It's actually very interesting in terms of there's this Doria-Frey approach to twisted supergravity, and they have a whole something like on the NLab, which is like this M-theory Lie-3 algebra or even M-theory Lie-6 algebra that should describe the ghost action of twisted 11-dimensional supergravity. And that's all governed by kind of singlets in Chevalley-Eilenberg cohomology. There's another thing you can do with the Chevalley-Eilenberg cohomology is you just compute Chevalley-Eilenberg cohomology of supertranslations. And instead of looking at the graded pieces of Chevalley-Eilenberg cohomology, you can consider that cohomology group as a module over the nilpotence variety. And these modules give you an input to run this generalized pure spinor formalism and construct non-trivial modules, just like we constructed the 6D hypermultiplet from a non-trivial module. So that's the second application of Chevalley-Eilenberg cohomology. And I should say, I'm not sure that where exactly it's written down. Of course, there's a lot of work by Movshev and Schwartz and collaborators, but for 11-dimensional supertranslations, there's actually only 3 non-trivial Chevalley-Eilenberg cohomology groups. And in particular, they're of ranks 1, 2, and 1. And the top Chevalley-Eilenberg cohomology is like a shift of the 0th Chevalley-Eilenberg cohomology. And you can start imagining things like taking the second wedge power of the first Chevalley-Eilenberg cohomology, and that gives you a map to the second Chevalley-Eilenberg cohomology. And so using the second Chevalley-Eilenberg cohomology is very similar to a volume form on the nilpotence variety. And so this kind of gives you a hint of how you can understand pure spinor actions geometrically.
So Richard, maybe you mean like with respect to a particular totalization of the degree, right? Because I think this cohomology is going to be of infinite rank over the field, but it's going to be like a finite rank as a module over this ring, which ends up in degree 0 after you totalize.
Yeah, it's a rank of the, yeah, so that's what I was trying to make the distinction, where in a lot of literature, people think that Chevalley-Eilenberg cohomology as a graded vector space, and it has an infinite number of graded pieces. And you're right to give this warning, but if you consider it as a module over the nilpotence variety, that module will have finite rank. And I should say that sort of looking at this infinite, looking at Chevalley-Eilenberg cohomology as an infinite dimensional graded vector space is kind of primarily how it appears in the literature. And we're hoping that viewing it as a module, it has more geometric structure and we can kind of extract a little more mileage from it this way.
Actually, we have a paper with Simone Snoia and other people about Chevalley-Eilenberg cohomology for superalgebra, super translations. Actually, where we show indeed how you get a finite model, so where it comes from. So it is a whole structure in it. I mean, it's very clear what happened. You don't know it.
Yeah. Yeah. Okay. Yeah. So it has appeared in several places, but I just want to emphasize that this is a very useful approach to Chevalley-Eilenberg cohomology. Maybe the last thing I should say is there's very surprising things, and maybe for mathematicians or even physicists, I think there was a paper of Howe and Berkovitz where they consider, so for example, Chevalley-Eilenberg cohomology of 10D n equals 1 supertranslations has a very beautiful structure. The first Chevalley-Eilenberg cohomology group, roughly speaking, has rank 5. And you can approximately view the higher Chevalier-Eilenberg cohomology groups as the exterior powers of this rank 5 module. But it's not quite true on the nose, and it's related to the fact that, not all these, that there's certain kind of exceptional cohomology groups coming from Borel-Weybot that we don't fully understand yet. And we had a list of trying to understand these Chevalier-Eilenberg cohomology groups, like Chevalier-Eilenberg, the second Chevalier-Eilenberg cohomology group is supposed to be related to the current multiplet for 10D n equals 1 supersymmetry. And so if you have results on Chevalier-Eilenberg cohomology groups that can compute them, it'd be very useful for constructing multiplets.
Other question? So earlier you said that this variety have canonical volume forms, right? So
yes.
What do you mean by that? Like they are, say, they have a trivial canonical sheaf?
Not all of them. So for example, P3 times P1 has a non-trivial canonical sheaf.
Well, yes, of course, it's a Fano manifold.
Right. So yeah, what I mean is that even so we write everything in terms of, sometimes it's easier to talk in terms of the cone and to look at the dualizing module. And so in certain cases, like 10D n equals 1, there's a very beautiful like bundle, which is something like O8, or I think either O plus or minus 8 over the orthogonal Grassmannian 510. In the total space of the bundles Claviau, so you have kind of a natural Claviau volume form on the cone over. So the cone over space of 10-dimensional pure spinors is Claviau, but in general, like 60 n equals 1 is only going to be a Cohn-Macaulay ring. And so there is, but still you can use the duality theory to cook up certain pairings in these other cases. But I admit it's the best situation is when the nilpotence variety, the total space of the nilpotence variety is Claviau, or some sort of singular Claviau, which is known as Gorenstein.
Okay, so you use some kind of a local Claviau structure or something. Yeah, so there's both the nilpotence variety and there's an affine nilpotence variety, and then it's projectivization. And the affine nilpotence variety has this singular Claviau structure known as Gorenstein. In certain cases, like 10D n equals 1, but in other cases, it's not Claviau or not even Gorenstein. So it really depends on the algebra in question, and it's related to the types of interactions you can construct. Okay, thank you. Other question? So if there are no further questions, I will thank the speaker again.